The C-sharp relational operators are designed to give us valid Boolean expressions. So we use these to compare values against other expressions, literals, or values. For example, assume that the value of x is 50. Well, I have a series of Boolean operators that I can use to evaluate x in terms of another value. The double equal sign, or equal equal, is my equality comparison operator. So x equal equal, usually pronounced is equal to 50, that statement would be true. The exclamation point is a negation. So the exclamation point followed by an equal sign means not equal to. So x not equal to 50, that would return a false. We also have the standard less than and greater than signs, and they behave as you would expect. The less than and equal to is the less than sign followed by the equal sign, and then we have the greater than equal to as well. And those behave the way that you would probably expect. Now, logical operators are used to build more complex Boolean expressions. So we can take multiple Boolean expressions and then create larger, broader expressions out of these. We basically have three general logical operators. We have our AND, our OR, and our XOR operator. Now, the AND operator, represented by the ampersand, is a way that we can test to make sure that one Boolean result and another Boolean result are both true. If that's the case, then the entire expression is true. There are two versions of the AND operator. We have one with one ampersand and another version with two ampersands. The difference between them is that the one with the double ampersand provides what's called a short circuit evaluation. In other words, if it can determine by looking at one side of the equation or the expression that the expression is not true, then it doesn't even have to evaluate the other side. Look at this example. If x is equal to 4 and y is equal to 6, then I know the entire expression is true. So if I were to evaluate the first expression, x is equal to 4, and this is false, is there any way that the entire expression could be true? Well, obviously not, because the only way for the entire expression to be true is for both sides to be true. Therefore, there really is no sense in evaluating the other side of the expression. So the double ampersand provides a short circuit evaluation. If x is equal to 4, it returns a value of false, then y is equal to 6 will never be evaluated. The same thing holds true with the OR. If x is equal to 4 or y is equal to 6, then the expression is true. One side or the other has to be true. So I know that if the expression x is equal to 4 is true, then it doesn't matter what the other side says. Y is equal to 6, that could be true or not true. It makes no difference. So it only has to look at the first side of the equation. So depending on whether or not you want the short circuit evaluation, you can either use the single or double ampersand or the single or double vertical bar for your AND or your OR. The XOR operator is a little bit different. The XOR operator, or the caret, is an exclusive OR. The exclusive OR allows us to identify exclusively one side or the other being true. So x is equal to 4 or y is equal to 6. One or the other, but not both. If that's the case, then there's no way that you can look at one side of the equation and determine whether or not the other side is true. The entire expression is really contingent on the other side. So we do really have to evaluate both sides in this example. Now we also have a standard set of mathematical operators as well. The plus, the minus, as you would expect, the asterisk for a multiplication, and the forward slash for a division. We have an increment operator, the plus plus, that we use to increase the value of an operand by 1. This is a unary operator. It operates on a single operand. So the x plus plus, as an example, would increase the current value of x by 1. Assuming that the current value of x is 5, x plus plus would result in 6. Now we have two options on how we use this increment operator. I can either say x plus plus, or I can say plus plus x. Both of those approaches will give me the same ultimate result on the value of x. X will increment by 1. The difference is whether or not an expression that's evaluating to the value of x plus plus will return the pre or post incremented value. For example, assuming that the value of x is 5, if I were to set y equal to x plus plus, what's the value of y? Well, in this example, the value of y would be 5, because we're assuming that we are assigning before we do the increment. Y equals x plus plus means assign, then increment the value of x. If I were to say y equals plus plus x, it would be exactly the other way around. Now it's increment, then assign. So y in that case would be 6. Plus plus x increments 5 by 1, but the result of the incrementation would be assigned to the variable y. We have the same thing with the decrement as well, using the minus minus operator. We also have shift operations as well. So if you need to do bit shifting, we have a right shift and left shift operator. Basically what this does is just take the bits in the actual binary value and shifts those to whatever number of places you specify. So a 10 right shift 2 would give me 2 as an answer, where a 10 left shift 2 would give me 40. The percent sign represents a mod division operator. So that's the remainder of a division. 10 mod 3 is a result of 1. Or in other words, 10 divided by 3 gives me a 3 as a result, but I have 1 as a remainder. So that remainder is the value of the mod. I also have a ternary operator, a question mark and a colon. This is basically like an immediate if. I have an expression that I can evaluate, and then I can do two different things depending on whether that expression evaluates to true or false. So the question here is if x is equal to 2, then x plus plus. Otherwise, y plus plus. Do one thing if it's true, another thing if it's not. I also have a series of compound assignment operators. These can be incredibly convenient when you want to add something or subtract something and then reassign the value into the original operand. For example, x plus equal 5 is functionally the same as x equals x plus 5. In other words, we're incrementing x by 5 and reassigning back into x. There is a compound assignment for virtually every mathematical operation.